Introducing the speaker. So, talking about object recognition as typically, for convolutional neural nets has been on the cloud or very compute-intensive environments. So what is very cool about tonight's talk is you'll be talking about how it can go to mobile and IoT and much smaller platforms for not just the scoring, but also the learning is the promise. So that should be definitely very interesting. He's a co-founder of Aipoly. So please help me welcome our speaker, Alberto Rizzoli.
Good evening, everyone. I'm going to be turning my mic on and see. Yeah, that's great. Good evening again. Here?
Whatever's good for you.
Yeah, that's probably not going to sit. Thanks for coming to this talk. I know that a number of you are from the deep learning group, so the first half of this, for a few of you, is going to sound like old news. So bear with me. At the end of the talk, we're going to have a Q&A. And if you're not satisfied by that, my email is simply alberto@aipoly.com. This is also for the recording. If you have any questions regarding our work, technical or non-technical or partnership related, feel free to drop alberto@aipoly.com an email. So the story of my work at Aipoly actually started in the accessibility sector. Particularly in the field of blindness, which is going to be a topic that's going to be thrown around in some of the examples that I'll be presenting. In particular, in trying to assist people who are blind or visually impaired with identifying objects and using deep learning. So this started, for me, this project started only about a year ago. But for those who are not too familiar with deep learning, it started many decades ago. It's not such a new technology. It started in the 80s, but even before that, the roots of it come, like all great technology stories, with a cat. It all started with a cat. In particular, a cat whose head was stuck in an experiment to understand some principles of computational neuroscience by putting an electrode into the brain of a cat to record the signal of a neuron. This is an experiment by Hubel and Wiesel. The date is 1962, so a long while ago. The cat was fixed into a machine, electrode into the poor animal's brain. He was put to sleep with some sedation, and then he was shown videos, not quite YouTube videos, something a lot more boring, which is this line passing in front of the row of X dots. As you can see, when the line passes through it in a certain orientation, only the one following the alignment, the parallel alignment of the dots, you can hear the neuron spiking. That faint crackle was the moment in which we understood a lot more of how the visual cortex works. This experiment won the Nobel Prize. We tried again on monkeys, and we had very similar results. We realized that neurons were firing not to, very articulate scenes, but started by firing to simple shapes. That reminds us of a Gabor filter, one of the basic principles of computer vision. And then we found out by exploring more of the visual cortex that this hierarchy actually expanded deeper into the brain. So those neurons that first identified that little row of X's were connected to neurons that would identify more complex blobs and unrecognizable shapes that then would go deeper into a hierarchy into more complex figures that can be identified as things that we recognize in the real world. And that reminds us a lot of a neural network But meantime, at that time, we were using very different systems for computer vision. For example, SIF algorithms that try to match the different areas of a picture to those of another. In this case, it's recognizing that card in the picture, but it doesn't work very well if you want to recognize something like a human or a panda or something that's three-dimensional and comes in different shapes and sizes. Or pictorial structures, which is essentially understanding a human as a series of blocks. This is my arm and this is my chest, connected by springs. And if they don't vary off too much, if my arm doesn't suddenly fly off to one side of the screen, the computer can basically understand that there's a human being there and that he or she has limbs. These systems were not the most efficient. You can immediately understand the limitations of a SIFT algorithm here in trying to identify these plates. You have to run it, try all kinds of different items, and only if it will perfectly match, you'll have an understanding of the physical world. And so things started to change in 1980 with Kunihiko Fukushima. He created the very first neural network. He didn't use backpropagation. The first one to do so was Jan LeCun. And this is the architecture of LeNet, a very famous architecture because after he inserted backpropagation, this particular net was used in recognizing lots and lots of checks. This is a video from 1983, even though his paper is from 1989, where this first example of a neural network with backpropagation is recognizing numbers, handwritten numbers, and numbers with the handwriting of a doctor, circular things that previously could not be done in computer vision. So this was in 1983. And since then, neural network had kind of gone into a slumber. It was only until 2011 at the ImageNet competition that they had a sort of rebirth. We can see the very stark improvement in its results by taking that architecture of LeNet from 1983 and reapplying it with modern GPUs that have been evolving thanks to gamers and their thirst for better and better gaming graphics, and thanks to data because we've created a ton of it, and the ImageNet database, which is a data set of 1.2 million captioned images that were perfect for training this kind of network. We realized that the previous computer vision systems that we were using to score highly in the ImageNet competition were quickly going to be overwhelmed by a deep learning system. And that big improvement between 2011 and 2012 carried on, and we're currently beating human performance to the point where we don't even consider this competition to be fair anymore for humans. The main improvements, as I said, is data. We've created 10% 90% of all the data in history in the past 2 years, and we're now at the point in which these deep learning systems for vision can create full sentences. This is a neural image captioning from a famous paper by Google, and it's able to identify not just these pictures, but also what's in them and create a sentence to describe them. In Aipoly, this has been part of our research in trying to give the blind a very contextual understanding of where they're in. It's been one of the biggest problems in computer vision to actually create a sentence out of a photo. It currently doesn't work well enough for someone who has no other way of cross-checking what's actually in front of them. But this is sort of the dream of what we want to achieve one day, have a perfect understanding of the physical world so you can actually ask questions. There are a few other areas in which deep learning has now beat human performance. Recognizing sketches, we're now at 70% accuracy against, I think, 68 by humans. Cancer nodules in the lung, 50% better better accuracy in diagnosing cancer
nodules by analytic compared to a panel of expert radiologists. Facial recognition, we're now on par with humans. This is Facebook's deep face, so we're tied on there. And then there's all kinds of wacky use cases. If you want to make $1 million today, you make an app that applies Van Gogh styles to your videos and pictures. And that actually happens. You can download Prisma or Picasso app, and everyone's going crazy with these. They're a lot of fun. So we're currently at a stage in which, in David Marad's stage of visual representation, which is kind of a scale in how well we can represent the physical world through sight, we're somewhere between the 2.5 dimensional sketches and the 3D model representations, where to actually mimic the way we humans understand sight, we actually create a 3D model of what we see in our brains. And then a lot of other feelings fire. When you imagine, for example, if I tell you lasagna, you might be thinking delicious. You might be thinking like, oh no, I'm vegetarian. And you might be imagining a 3D representation of the word that I just told you. Computers can do that halfway. As you can see, for example, the previous slide of deep face, we use a semi-3D representation of someone's face to improve recognition. But currently, what's state-of-the-art is image parsing. And here's an example from the eLab at Purdue. This is done by Professor Eugenio Currucello, who has been essential for our work in Aipoly. And this is running on a MacBook Pro. It's a net from around 6 months ago. And it's able to parse chairs from tables, from a number of classes of furniture in real time. So this is a computer that's able to gain sight that's almost comparable from what we humans can do. 6 months later, a new version is out, and this one's quite incredible in my opinion. This is running on Tegra K1, which is a chip that is currently, if you guys can go to Google Tango's website, it's inside this little tablet kind of device, and it's a chip that is essentially made for mobile computing. You're able to get an understanding of the physical world. If you can see the actual space between the legs of the human figure there can be distinguished. And this is sort of a way of making end-to-end deep learning robots and self-driving robots and all kinds of other cool technologies that are not going to be relying on the cloud because they essentially need this real-time recognition. Which is important because 60% of everything that we humans perceive comes through sight. So if we're able to understand the physical world very, very well, if we're able to understand motions through sight, then the most important sensor in people's mobile phone is going to become the camera. Because while today you pull things from the cloud, you are able to tell from the accelerometer that you're running and do these kinds of clever extrapolations. If you actually want an AI to solve a problem for you, one of the best way to do it is to actually just point at it and say, solve it. And that could be dirty dishes, or that could be, some math problems on your notebook, or that could be, a bunch of food on your counter from which you can create a recipe by simply understanding what's in front of you. So there's many different possibilities from bringing this kind of object recognition to small devices in real time. We in particular created one for the visually impaired. As I've already introduced, Aipoly is an app currently used by 100,000 people, aimed at people who are blind, so that they can have a real-time understanding of certain objects around them. The app that you can currently download from the App Store has a model for 1,000 items recognition. We're now bringing that up to 5,000, introducing a whole number of new items like supermarket items and food. And I'll be talking later about how sort of this has taught us a little bit more of the perils and the challenges of bringing deep learning into the mobile space. The first example, though, of deep learning on mobile for object recognition wasn't us. We were kind of the second, starting in January 2016. The first was probably WordLens, which is now owned by Google and known as Google Translate, where they did something really clever. In order to do this OCR in the wild, in order to recognize the characters on a pizza box, they created a system to create a data set of dirty pictures with smudges on them, pictures with bad lighting, so that they could then train all these letters for a neural net that would then run on your mobile phone in real time to read things and translate them in real time. So this was for text. We then evolved that into objects. And there's a whole new suite of startups that are starting to get into the space and recognizing. Some of them are doing motion, some of them are doing smart dash cams, where you can simply put your phone on the dashboard of your car and recognize potential threats. So what will this mean for the future? One exciting possibility, in my opinion, of bringing deep learning into mobile devices is the ability of increasing resolutions from screens. So if you're streaming the content on the left, you can use a network to actually improve it and bring it to a crisp, clear, the crisp, clear example on the right, which has been generated by a computer who has never seen the person on the left. In fact, the ground truth is slightly different, but that's good enough for me. If you give me a very crappy data stream and I have to look at the one on the left, I would much rather look at the imagined version that's in the middle right now.
Do they have a mirror version of that?
Oh,
a mirror version? Like,
there you go. That's the next big thing, I think.
Who's doing this?
I'll show you. This one in particular is by a company called Magic Pony. It's a startup that got recently acquired by Twitter. I'm sorry. And this is my favorite example because they actually taught it the user interface and the game elements of League of Legends, so that you can get a very bad stream of League of Legends, bring the resolution up, and if you're streaming 360p, if on the other end there's a network that can increase that resolution because it knows the game, then you don't need that high-speed data, you don't need that constant reliability on data. You can simply ramp it up on the other side. It's generated, so there may be some mistakes. We haven't seen them because they probably don't publish that many of them. But it'll be fun how this evolves. This has a lot of potential. On the other side, in augmented reality, if we... This didn't need to add audio, but... as you see the examples of scene parsing, where you can actually see the contours of tables and chairs, you can actually apply that to augmented reality on your mobile devices. Because if you can understand where a chair is, where an obstacle is, you can have creatures interact with the world. You can have elements interact with the world. The previous example that I showed is Google Tango, which uses a light sensor. That may be obsolete in a few years if we have deep learning systems on phones that can parse scenes in real time, like the ones that we've seen earlier. And then finally, for building new hardware, vision processing units are becoming a big thing. The probably most relevant one is by Movidius, where with 1 watt of power and multiple cameras running, you can run a neural network with real-time identification around 30 frames a second. That means if you want a drone or a little robot or even a toy, because these things are getting very inexpensive, that can recognize objects and teach your 5-year-old child about the physical world, you can do so in a thing that lasts the whole day. And they're also providing this as a sort of a compute stick. So it's a USB stick that supercharges whatever device or single board computer you connect it to. It's compatible with Caffe and TensorFlow, so that gives you an idea of what frameworks you might want to be aiming for. I have no affiliation with them. We personally use Torch. Yeah, TensorFlow in particular has been a favorite for a lot of projects on mobile. So the big question is, why not just use the cloud? And the first reason, there's three reasons mainly for this. The first one is that if you want to have a natural response time, you want something that runs in real time, saves you a lot of frustrations, and actually creates quite a big difference. Second is frequency of use. It will make you broke if you need something in real time. Third one is data. By natural response time, I mean that if you, oh boy, this is all, just gonna skip through all of them. If you ask Siri a query, it will take around 1 second to reply to you. And that's not exactly the best way of doing, of interacting with a human being. If you show an AI a picture and tell them to solve a query and they're using the cloud, they'll have to upload that picture, wait for a response that usually takes around 250 milliseconds to send a picture through a neural net and get a result, then send it back, and then tell you what's there. That will feel very unnatural. And we tried it with the real-time systems, and it feels a bit like talking to someone who has just woken up. So it removed from the experience. It was not the best case for asking an AI, what item is this? And if you can do it locally, you can beat human performance. We've tested, if you put a person in front of a screen with a rolling video that shows all kinds of animal passing through it and all kinds of items, and you tell them in real time to try to tell you what's on the screen. And then on the other side, we had an iPhone running a neural net that was looking at the screen, and the iPhone could do around 7 notifications every second. The human being could do around 0.8, 1 every 0.8 seconds by also communicating it to you. And so that's exciting. We'll get robots with a much quicker sense of vision and a much quicker way of reacting. And then the more obvious ones are frequency of use. If you're relying on an API and you have a fridge camera that allows you to check in and check out items, or something that will count calories for you and use it 3 times a day or use it many times a day and keep on using it. If you have a augmented reality app that continuously has to run on the cloud for identification, if you have a security camera that can identify people or strangers or different types of cars, you obviously want that system to be on the device and not in the cloud. The last example there is a Starship Robot. It's a semi-autonomous delivery robot that could make use of a lot of deep learning systems, especially it's basically like a tiny self-driving car. If it uses only one camera or a number of cameras and scene parsing, it could drive on its own. These experiments have been done many times. And then finally, data. Everyone's competing for it. If you want to stream an entire video just to identify what's on it, it's not the most efficient thing. In my experience with Aipoly, as I said, it's been a year in which we've started this project. Has mostly been that users really want to trust your object recognition system, especially if they can't actually see. And so one of the most cozy advantages normally of having a neural network that can suggest you what items it's looking at was obliterated for us. Because rather than being able to give you suggestions of what it's seeing, like most APIs do, it's telling you, I'm seeing indoors, and possibly there's people, possibly there's chairs, and possibly there's a tiger in the room. It's simply going to tell you, the number one thing. It's either that or nothing for someone who has, you can tell someone who has no way of cross-checking that what's in your plate is either a banana or a giant caterpillar. And those examples can happen. And so reaching very high accuracy has been very, very challenging. But it's been very rewarding. We've, as I said, we've marked 100,000 users so far. This is one of our first. This is...
Oh gosh, yeah. I mean, like I've got a pair of earphones here. Do you think it would...
Our very first MVP.
Right. You are looking at a new Apple earring. shocked.
So it's also been very rewarding as a journey. We've met lots of really awesome people that have sort of built this with us. A lot of Aipoly's data set is powered by the crowd. We receive submissions of pictures to train new items every day. And yeah, there's going to be an update on this quite soon that I'm going to show you later in the slides. One other reflection is that making everything run locally is sometimes overkill. Just like sometimes when you identify a plant or an item that you're not too sure what it is, you could check out on Wikipedia or you could Google it. Likewise, you could do it with AI. You can have a layer that is on the device that's able to make a primary filter and tell, oh, there's a person there, or there's that's a flower, and then it can check on the cloud what species it is. And if it can do that first filtering on the device, then it can greatly reduce the need of actually making API calls. So you don't have to check, whether every time whether you actually have to investigate something further. And the second one is every time the AI misidentifies something, we pretty much began losing a user, particularly in the field of visual impairment. And so having the right data set, the right architecture has been quite essential. And finally, one big suggestion I would give is to complement the user's intelligence. People have a tendency of using these object recognition devices to gain an understanding of what's in front of them, but they will always be willing to give some input to the AI beforehand. And one of the biggest requests that we have is, allow me to do a first filtering. Don't let the system try to identify that there's people in front of me. I just wanted to tell them whether they're there or not. So adding a first filter where you tell the AI, hey, is there any of these items here? And then it can create a filter where it can tell you, yes, I actually see there's people in front of me, there's this item or there's that. On big news, something I wanted to show you is a project that has been just published today, so I'm allowed to show you a video of it, which has been putting our system into a wearable. And this was a pair of glasses that are connected to one of the user's phones, and they run a neural net that in real time would identify items in a supermarket. It was trained on particular supermarket items. It had 5,000 classes. And yeah, so here's a quick demo of it.
I mean, it takes me forever to go grocery shopping. Even with someone helping me that has known me for years, I'll say, what's in that cabinet? What it was, develop a system, right to left, top to bottom.
Oranges. Sorry, I like it. Apple, grape, carrot, look good, lilies. Lily? Okay. All roses. Can I take this home? Okay, roses. Okay, tulips. That's awesome.
Seen it? Made. Coffee made.
Yeah.
Okay. It didn't say coffee, but it kept saying made.
Made.
Yeah. Not made.
Glasses, and right away told me there was the apple, and there was the oranges, and there was this, and there was that. And I said, this is great. Here's that,
So if you're a researcher, this is the stuff that your research is helping with. For us, it's been it's been quite an achievement. This is mostly where we wanted to get with using deep learning to try and give those users a bit of a superpower, a bit of an edge in their disability. And the last element that has contributed to it has been users. So if you can download Aipoly Vision, you can actually teach it new items. There's a button on the app that allows people to propose new items to teach it. And yeah, I hope you do so. I hope that you've enjoyed the talk. And if you have any questions for me, it's alberto@aipoly.com. And thank you very much.
So raise your hands. We can pass the mic for questions.
Very impressive. I'm wondering, like, does this app actually drain the battery?
Yeah. So it's been one of the biggest challenges that we've had. The battery drain for running this neural net on a phone is huge. If you don't do anything about it, you can reach 140% of the use of the CPU. If you use OpenCL, if you make your architecture more accommodating to the kind of phone that you're using, then you can reduce that. Yeah.
Have you tried to like comparative network, which reduce the computation required for recognition, like to paralyze the network?
Compressing the model?
Yeah.
We haven't tried that yet, but it's something that we can give a shot at.
There's a question here.
Hi, great presentation. This is very inspiring. You mentioned that you prefer Torch over TensorFlow. Can you explain why?
When we started, TensorFlow wasn't announced, and but yeah, our port still runs a lot faster than what we've been able to achieve on TensorFlow, and the speed of it has been very helpful for a variety of reasons, like using a moving average to make a better identification. But yeah, mostly been speed and what was available when we started off.
Hi, that was an impressive demo. Two quick questions.
Yeah.
So what do you store locally on the device versus what do you actually store in the cloud? Do you store like the models, the representation of the models?
Yeah.
Or do you have something else on the device per se?
The model is on the device. It's around 100 megabytes. And we don't really store anything on the cloud other than what the user submits. So you can run it on airplane mode, which has been one of the challenges because a lot of people who are visually impaired use airplane mode to for a number of reasons. One of them is saving battery. The other one is having more reliability on the phone. And yeah, so it's supposed to run entirely cut off from the internet.
Okay, impressive. That's. Have you experimented with the new neural network primitives that are available on the new iOS 9?
Yeah, we are.
Does that accelerate the learning process, or how is it?
So I don't think there's anything that we've achieved so far with that. I don't think they're that open for other apps to make use of. Yeah, but drop me an email. I could check out if we've achieved any results anytime soon.
Hi, my name is Akbar. I'm with Optimizing Mind. I thought I heard you said earlier learning on the phone, but let me also more generalize. I'm curious, how long does it take to update your model, in the cloud and so on? Is it days, weeks?
Yeah. We do the learning on the cloud. I mean, we don't do the learning on the phone. And we push a new model as an update. So the app updates with a new model inside of it, which means it's a fairly large update every time. It's about 100 megabytes or so. So we're only able to do it once every few months, or whenever needed.
Hi, my name is Wenxin. I'm a graduate student from Princeton University, far away in the East Coast. I have a question. What's the difference between the mobile deep learning and, for example, the ImageNet neural networks in terms of the implementation? Like, do you want to use less memory? Do you want to use shallower network to just fit for the mobile device?
You want to use, less power, essentially, and you can run an ImageNet, like a neural net trained on ImageNet on a phone easily. What you'll get different results because of the nature of the data set, and depending on how big and how deep the network is, you could get something that is either too large or too power hungry.
Yeah, but I mean, for example, ResNet has kind of millions of parameters, which needs a lot of memory. I'm not sure, like, if memory usage or CPU usage, like in terms of computer, is related to the battery usage of mobile phone.
Yeah, so we can run ResNet, I think ResNet 18 on mobile. The most power hungry part is the matrix multiplication, which we're trying to relegate to the GPU of the phone and try to do it in a less power hungry way.
Greg Mikowski, Ligadata, question. Let's say I'm a blind person and I can contribute to the general learning of the overall system. So here's an empanada that maybe you don't have in your database. But maybe I want to train on a relative. And I want to train that person's name, and I don't want to share that, but I want to know that for me to be recognized. Is something like that in the option at some point?
Maybe at some point, not right now. What we imagined was that you can simply, on the device, you can replace one of the classes that the net responds to with whatever you want.
Sure. Swap something out that hasn't been used by that particular user. And
swap it out. But it's not something that we'll be offering anytime soon. We'd rather have something where contributes to everyone else and is fairly curated than something where people can run wild. And
I'm assuming like a few point things of personalization, not broad, but okay, thank you.
So my name is Ed. Actually, I'm working on my own startup. I have two quick questions. One question is, how do you solve the bandwidth bottleneck, bandwidth, uplink and downlink? And the other question is, what kind of technology stack or architecture you're using? Is that a multi-tier or two-tier, like a mean stack?
I don't know if I can talk about the architecture that we're using.
Okay.
I don't know what you mean by the
mean stack is two-tier.
No, by the bandwidth.
Bandwidth, because when you try to download your trained model from the cloud, if it takes time, it also takes it's consuming bandwidth.
Yeah.
So how do you solve that? Is that a kind of challenge?
It hasn't been so far. We only push updates every so often.
For example, the car is moving, the mobile phone is the car is moving with the tree.
Yeah. Well, we'll only download it on Wi-Fi. But essentially what we try to do is, No. You only download a new model when there's a significant number of improvements to it. So it runs always on the phone. Then, 200 items are added or so. Or, 200 items are improved. And so a new one gets downloaded.
So no web access will not be sort of feasible. For example, I'm on the road. There's no Wi-Fi in the town.
Yeah.
I have mobile connection.
You'll still be able to use it, but you won't be able to update it.
Hey, my name is Tarun. I'm a product manager at Benetech. So maybe I missed it. How do you do the filtering of all the labels that you get from your neural net? Say, for example, you're looking at a scene. How do you filter it down to one label?
Good question. about to launch a newer system where you can actually just use some predetermined terms for it. Currently, what we've done is we've asked users to submit like a description sentence with for the photo that they submitted, and then we extrapolated the most common nouns in that picture. But yeah, that proved to be, if you give too much users if you give too much freedom to users to submit their own training content, then they start submitting pictures of their friends, and it can go far further. So we're only allowing a few thousand classes that you can actually use, and you can propose a new one, but you have a ghost proposition. So if you say, hey, I want to teach empanadas, you'll be the only one who's able to see that you're actually training on empanadas until that gets approved.
Hi, my name's Stephen. Had a question. How do you calibrate the sort of confidence and ambiguity threshold?
How do you calibrate the confidence?
Yeah, like the confidence threshold and the ambiguity threshold below which you won't detect.
Oh, okay. Depending on the model that we've used, we've had different results and different threshold, but we've normally set a base threshold for all classes, and some classes that have always been particularly giddy, we've set customized ones. Examples of that is toilet, which shows up if you show a lot of things are white porcelain items. And it's, to someone who's sighted, it's like, ha, this is toilet. But to someone who's blind, it's a more serious thing. And so for these kind of things, we've had a customized set of thresholds for it.
My name is Rob. As a human, looking at the learned things from your system, have you seen any patterns that have emerged that are interesting to humans from the different classes or something else?
As a human, any pattern that have emerged in you recognizing things? No, not really. I would say probably in having worked with people who are blind. Not really. Could you give an example of who are you thinking about?
Something surprising. Sometimes there's a pattern that emerges from the data that you're not normally thinking of ahead of time, right?
Yeah, don't make a class for walls. And a lot of animals can be confused for the wrong one by a wide margin. A lot of cats are tigers. A lot of rugs are cats. So there's that. And as I said, a lot of porcelain items are toilets. A lot of keypads to enter and exit doors are ATMs. So there's a lot of these things that for us, there's that contextual understanding. Hey, I'm in a kitchen. There couldn't possibly be a car in here. But the neural net's like, I saw a plate. It's round. It must be the wheel of a car. And so it says wheel. Those things can happen. So there's a few things that we're still far superior. It's a lot like you're suddenly taking a tiny child and suddenly opening his eyes to a completely brand new scene and telling him, identify. And he's like, I don't know. It's it's telling you there's this. I see this shape, and so I'm going to assume that you're in a parking lot. There's a few things that can be done around that.
Hi. Carl here. I was thinking of two other reasons why you don't want to use the cloud. One would be privacy.
Yeah.
And the other one is in deal with disasters, cloud might not be there. So, I imagine in a lot of cases it might be emergency situations it would come in handy for.
Yeah.
Did you thought about adding, we was talking about competence levels, is there qualifiers you might add to something saying, I think it's this, or, it's probably.
I think it's a cat or a rook.
Yeah, we have, so in the current version, we tested two modes. One that tells you it's probably it's most likely I have little confidence that it is a, and that was not the favorite, but actually giving someone percentages turned out to be something that some people enjoyed, some people just found it confusing. Yeah, so we've tinkered with that. We found that there's no better way of actually manually improving the recognition of an item. Yeah, and to speak to security, which I completely missed out, it is a big problem. Mattel, for example, created a Barbie version that had like a speech recognition system on it, and it would send all the utterances to the cloud. And it's currently the lowest rated product that Mattel has ever produced ever. Because of that, there's probably not much of a risk in there, hearing your child telling Barbie about her secrets, but people really do not like that. So having something that is local is definitely preferred.
Hey, my name is Michael. Can you hear me? So my question is, what is, in the current state, what is the minimum system requirements for your
Good question. I recommend probably the cheapest thing you can do it on, or not cheapest, but the least powerful is a Raspberry Pi 3. So if you go for like a 64-bit system, you can actually run a network on those. If you are thinking of that, get an Odroid rather than a Raspberry Pi 3 if you're prototyping with little things. And in terms of mobile phones, we've currently experienced mostly with iOS. So it's the least powerful one that we run our system on is the iPhone 5S. But most phones with an Exynos chip by Samsung or iPads, they should be able to do the job quite efficiently.
Yeah, so it looks like your system is in production. I'm just curious. Is your system in production? And what is the size of your training set? Is it keeping growing, or it's a sort of static?
Yeah, it's in production, so we do continuous updates. We don't push all of them, of course. A lot of the ones that we're doing now are experimental. But the training set does increase. Unfortunately, I can't, and it's stupid, but I can't tell you how large it is. But it's,
roughly, I'm not
taking ImageNet as
a terabyte,
Yeah,
or what kind of roughly?
It's ImageNet sized.
So it's you do training in cloud, and that is like a public cloud or data center. What kind of cloud?
The data set is private.
Okay. Yes. Thank you.
No worries.
Hi. My name is Cyril. I saw in the video that you were mostly giving objects which were one at a time. Have you considered there's a dog and a cat both sitting together, or a child and a teddy bear sitting? What will it identify? Does it do object segmentation and tell that this is a dog and this is a cat, both of them? Or?
Yeah. Right now it doesn't do object segmentation. There are some, if you look at, for example, there's one called YOLO, You Only Look Once, on papers that can do multiple classes and segment multiple items of these classes in a real-time video feed. But that was a bit too power hungry for us and too few classes. Right now, if you show Aipoly two items next to one another, it will show number one item as the most probable, number two as the second most probable. I think my mic cut off, but I'm just going to speak up a little bit. Yeah, I'm afraid the battery. I have a spare, but apparently we're here to get we're going to be focusing on recognizing one item at a time. I'd love to have more, and I'd love to have actually a semantic simplicity in this right.
Hello. So I'm assuming the light can actually do away with without light, but this technology needs the light in their house, and how sensitive is it to different lighting in the house and those kind of things? Can you talk a little about that?
Yeah, good question. Light can throw things off, especially if it's many different points of light for certain items. Low light is the bigger problem. So currently we have a system where if the camera detects low light, because some people who are blind might enter a room and it's completely dark and not really care. The phone's torch will automatically go off and turn back off when there's enough light for it to see. But the noise of low light and the bad definition of a camera in low light can be an issue.
Hi,
You can train for that.
Hi, this is Fei. I have a question about this computation. You said so right now you have the CPU and GPU. Which one consume a lot of meaning computation, like in CPU or in GPU for your app?
The one that's currently available does entirely everything on the CPU, which is a power-hungry solution. But you can offload a lot of the computation to the GPU and save almost 10 times the amount of battery life. That's something that we're doing right now.
So this is I'm Sudran, and actually follow up on a question that was earlier. You gave examples when the system can get confused, whether it's a cat, rag, tiger, etc. So is it something that is the result of limited training set? Is it because you have to compress the model to make it easier to run on a mobile device? Is it because you have to cut off computation because of the power? So what do you see as the key challenge, and how do you plan to overcome it?
Yeah, a lot of that is the training set issues. There's either not enough pictures of something, or it's coincidences. Like if you have a rug that really looks like a type of fur, it will completely ignore the actual span of it, and will think that it's a close-up picture of a cat. So one of the other issues that you could have is if you're training on a lot of close-up images and a lot of farther away images, and then putting them all into the same net, that you can have some issues. In particular, if you're using a data set of textures, then you could start seeing textures like something that is furry or something that is charcoal into other images that have simply an element of that. That can be a mistake.
Greg, question. Are you guys, people at your company, participating in the ImageNet competitions currently or in the past?
We're not.
Okay. Just spend your time. You've got your own.
Yeah,
okay.
We might.
Okay. Oh, last question. Can you tell us about how you got involved with the project for the blind? That's a great application.
Yeah, so we started this project at Singularity University, which is just across the water in Aipoly at the NASA Ames Research Park. And the aim of the university is to solve one of 10 grand challenges affecting humanity. One of them is health. And blindness affects 285 million people around the world. Severe visual impairment, that's less than 5% of your sight. And it's the most untapped disability, the most unsolved for disability, often because it affects the poorest among us. Thankfully, a lot of these people have been able to have access to smartphones recently. So, yeah, we're trying to reach those people with deep learning.
Okay. Well, we can maybe save further questions for directly with the speaker, but let's give them a warm round of applause.